In this lesson, we're going to work with properties of logarithms. Now, the two major things we want to work with properties of logarithms that are going to help us out, it's going to help us evaluate logarithms, especially if you don't have a calculator, or if your calculator doesn't have the choice where you can put any base you want. The second thing that we're going to majorly use these properties for is how to solve equations. And the solving equations stuff will come in 4.5, but knowing how to expand and condense logarithms is going to be really, really important in order to finish that goal. Okay, so when you're thinking of the properties of logarithms, the most important thing to remember is that logarithms are the inverse function of exponentials. So the rules of exponents still are going to apply, they're just going to look a little weird. Okay, so let's review a little bit of our exponent rules and then we'll talk about logarithms. So how can you condense two exponential expressions with the same base when they are multiplied? So if we have something with a base raised to a power times something to a base raised to another power, how can we simplify that? Well, since Algebra 1, we learned that we are going to add those exponents. Now, these rules are an equal sign, not a one-way arrow. So you should be able to work them backwards. So the next one says, how do you work with a base that has a sum as an exponent? So how can we expand that into multiple exponentials? Well, that comes from when you multiply. So again, it's just working with our property that we just had in the previous question. So it's a two-way arrow, and that's really important. And that gets in the idea of expand and condense. So let's talk about the property of exponents and then see how that relates with logarithms. So don't forget that logarithms are giving you the exponent. Okay? So in this first one we have right here, we see that we have n to the a times n to the b. We know that's going to be n to the a times b. So when you're multiplying like bases, you add exponents. So right here, the n to the a is actually that big capital N from Ben and Benny that we talked about. So that x is like that big capital N, and that y is like a different big capital N. That's like n1 times n2, just like we have here, n1 times n2. So we know we're going to add the exponent. Well, how do you find the exponent that you raise n2 to get x? You use a logarithm, log base n of x. Same thing for y, it's log base n of y. So when you take and pull this through, there's our property. So when you're multiplying the n, the number, in your Benny form, you're going to add two logarithms. Okay, so let's get this down as an equivalent over here. So we have these rules now. There's our new logarithmic rule. When you're adding two logarithms, you multiply the numbers on the inside. That condenses it. And if you want to expand it, you take whatever's being multiplied and you break it into the addition of two logarithms. You're adding exponent. All right, we got two more of these to go through. So how can you condense two exponential expressions with the same base when they're divided? So if I have a base to a power divided by a base to another power, from Algebra 1a, we learned that we subtract exponents. How can you expand exponential expressions when we have a difference for our exponent? So we're just working backwards. So this comes from, when you subtract, comes from when you divide like bases. And the 1 in the denominator is the one after subtraction. In Algebra 1 and Algebra 2, we learned that a negative exponent really means that it's going to be in the denominator. So it's really a plus negative c. So it'd be b to the a times b to the negative c, then which would drop it down here. So let's see how this looks with a logarithm. So when we're dividing like bases, so it's like that n to the a is x, and that n to the b is y. So when you're dividing like bases, you subtract the exponents. Exponent, I need to raise the x2 to get, or n2 to get x, would be log base n of x. What do I have? What's the exponent I have to raise n to get y? Well, that's log base n of y. So very similarly, we're going to take this, slide it through the magic tunnel, and we're going to see what it converts into. So we subtract the exponents. All right, let's just go take this and bring it down here and write down our two rules. So when you subtract exponents, it becomes dividing of like bases. It's using that exponent rule backwards. So if you're subtracting two logs, you can condense them down to one by dividing the number inside. All right, last rule. How do you condense an expression, or an exponential expression? So we got b to a power, so b to the a, raised to another power, so raised to the c. Well, from Algebra 1a, once again, we've learned this and doing it in 1b, we do it in Algebra 2. So when you raise a power to a power, you multiply the powers. Well, the next one says if you have an exponential expression who has a product as a power, how can you expand that? So we would take b to the a and raise it to the c. We're just using our first rule, the one we know well from Algebra 1 and Algebra 2, backwards. So let's take a look at this when we're dealing with a problem like this. So question is, remember that x is n to a power. Okay, so when we're looking at this, what we see in here is we have the x, which is n to a power, to the a. So we have a power to a power situation here in this problem. Okay, so the question is, what is that question mark? How do you find the missing exponent? Well, you turn it to a logarithm. So it's log base n of x. All right. So when you raise an exponent to an exponent, you simplify this or condense it down by multiplying the exponents, right? So what we're going to do is we're going to multiply the exponents. We're going to take the exponent a and times it to the other exponent, log base n of a. Or sorry, log base n of x. So let's bring this down and see our rules. So if you have a product here, this becomes a power to a power. All right. If you have a power to a power, remember, that's n to a power is representing x raised to another power. You just take this power and you bring it out in front. And that's what we're seeing over here on the other side. So there's our third rule that we're going to use for logarithms. They're based off the rules we already know. So on the left side is what we see in Algebra 1 and Algebra 2. On the right side, we started learning these in Algebra 2. We're supposed to be really good with them in college algebra. So when you see a sum of exponents, right here, it's the sum of exponents, you multiply the exponential expressions. Remember, x is n to a power, y is n to a power. When you divide exponential expressions, you're subtracting exponents. Okay? When you're multiplying exponents, that's coming from raising a power to a power. Some other basic properties we have the inverse properties that we already discussed in section 4.3, day 1. So we have our inverse properties. Inverse functions cancel each other out. So if the base of the log and the base of the exponential are the same, they cancel out, just giving what you have for your input. And then the other property we know from a long time ago, this is n to the 0 is always going to be 1. So if you have a 1 here, then you know the exponent is always 0. These are properties you want to know inside and out because they're really quick and easy to use. All right, so let's talk about how to use these properties to start solving equations. Okay, we're just going to barely touch on solving equations today. We're going to do a whole lot more of that in section 4.5. So what we're going to do is we are going to take this equation. The first way we're going to do is just use the definition of logarithms. So log base A, and logarithms equal the exponent, which is y, and then you put the other number right here. So we have y equals log base A of n. Well, let's try to do this with using any base except for A. Okay, so I'm going to go back to this first one and show you an alternate way to do this. It's another way to get the same thing. You could actually take the inverse operation. So A as a base, what I could do is I could use log base A of n and take that of both sides. I'm not multiplying it, I'm taking it. So we have this property right here, and we see that these cancel out, giving this statement right here. Okay, so let's now take a look at how to do this with using a different base. So let's use the idea of using a logarithm. We're going to take a log of these both sides, but I'm going to use any base other than A. So let me just call it base B. Just as a reminder, our bases are going to be positive numbers. No 0, no negatives, and no 1. Okay, so our goal is to try to get this y by itself. So the issue with it is we've got to get this power all by itself, and it's stuck in an exponent. So one of the techniques, the first technique we ever go to, is we try to use the definition of logarithms and rewrite it from exponential notation to logarithmic notation like we did over here. Okay. The other option is we now have a property that will allow us to take this power and drop it out in front. So that's what we're going to do for our next line of work. We're going to use the property. When you raise a power to a power, you multiply the two exponents. Well, y is an exponent, and the logarithm is an exponent. Now we just have y times something. We know how to solve for that. We've been doing that for a very, very long time. So now you divide each side by log base b of a. So there are two acceptable answers in this problem here. One when we're using the base of a still, and one where we can use any base we want. Again, our bases for logarithms have to be positive, and it can't be 1. That's the only number we don't use as a base. So let's talk about this concept right here. This right here was a way to get y written by itself, and this is going to lead us into our next major property called the change of base property. So it was kind of neat that we could actually solve a logarithm with any base. So let's go back to that previous slide here. So what we're seeing right here is we're seeing that we have this is y and this is y, which means these two things are equal. So the change of base formula says that our base goes to the bottom, like a basement. The base goes to the basement. Or for anybody who plays any sports, understands that when they say have a strong base, whether it's basketball, wrestling, football, you do it in softball, you do it in soccer, you do it in baseball, you're making sure that the lower part of your body is spread out enough, your feet are wide enough, you've got a strong base. Okay, so the base goes to the bottom. The n goes in the numerator, and you turn it into two logarithms being divided. This is called the change of base formula. Okay, so if your calculator doesn't have a button where you can put any base you want in there, your scientific calculators will only have base of 10 and base of e. So if you want to do log base 3 of 7, you'd have to convert this, where the log base 3, the 3 would go on the bottom, and then the 7 would go up on top. And then you can change it to the common log or the natural log and use your calculator. So let's talk about how to do these problems using our properties and not using a calculator. So 5 to what power is 375? Well, 5 to the first is 5, second power is 25, third power is 125, fourth power is 625. That's 3 point something. Don't know it. 5 to what power is 3? 5 to the 0 is 1. 5 to the first is 5. That's 0 point something. By 3 point something minus 0 point something. So my answer's got to be between like 2 and 3 something. I don't really know. So let's take a look at the key concept here. We are subtracting two logarithms. Logarithms are exponents. So what we do is we need to subtract our exponents. That comes from dividing the exponential statements. So we're going to take 375, we're going to divide it by 3. So this becomes log base 5, 125. And 5 to what power? 125 is the real question. Well, that's 5 cubed. So my answer to this problem is 3. No calculator needed. All right, let's try the next one. 54 to raise to a power of 3 or 6, that's irrational. I don't know what that value is. So what I'm going to try to do is try to condense it down and maybe get something I'm used to. So we have 2 times a log. So we got 2 times an exponent. So let's say, hey, we got an exponent times an exponent. So what I'm going to do is I'm going to raise the exponential statement 3 to the second power. And there's not much I can do with this log base 54 of 6 at the moment. Well, what's 3 squared? 9. Now that didn't really help me evaluate this. I still know at the moment that this is less than 1, because 54 to the first is 54, and this is less than 1. So it's something between 0 and 1 plus 0 and 1. My answer's got to be between 0 and 2. So what I'm going to do is I'm going to try to use that addition. So if I'm adding two exponents, that's what logarithms are, they are exponents, I'm multiplying the exponential statement, the number they're equal to. So 9 times 6 is 54. Well, that's log base 54 of 54 to the first power. We have a basic property. Or you can just say, hey, I know this one in my head, and I don't need to actually write the power 1 down there. And I can just know that it's 1 right at this point in time. So 54 to what power is 54? Well, it's 1. So this whole thing equals 1. The previous one was 3. All right, so let's go take a look at this one right here. Now, if the base was 10, this would be easy. It would be 3, but it's not. So what we got to do is we got to find a way to evaluate this. So I could, if I wanted to, is do 100 to the x equals 1,000 like we did on our worksheet, and I could work that out. And then I could take and divide that answer by 3. Another way is to think, hey, 1/3. I can make that a power for 1,000. Well, remember, fractions as a power are really radicals. So it's the cube root of 1,000, which is something I know fairly well. That's 10. Now we're taking 100 to what power is 10. If you feel more comfortable, you can make an x here. So now we have, what is that, 10 squared. So 10 to the 2x equals 10 to the first. So 2x equals 1, which means x is a half. So this original problem was equal to 1/2. Okay, let's try some more problems using these properties. When the log has a base that's not written, it means the base is 10. It's the common log. Now, if we do 1,000 as a power of 10, that's easy, but we got this extra power here, so I don't like that at the moment, so I'm going to bring it out in front. So now we have 20 times log base 10 of 10 cubed. That's what 1,000 is. These would cancel out. That says multiplication there, so we have 20 times 3, which is 60. Let's take a look at this one. So what we're doing here is we're expanding. The first couple of problems we were condensing. Now we're expanding. So this is a weird little fraction here. But I know 49 is a power of 7. I know the square root of 7 is a power of 7. So let me rewrite it. So this one is log base 7 of 49, which I'm going to rewrite as 7 squared, minus log base 7. So when you divide the exponential statements, 7 to a power, divided by 7 to a power, we subtract their exponents. So this now becomes log base 7, and the square root is the half power. So now I can cancel them out, or I can bring the 2 out in front, and then the logarithms would give me 1. So I bring the power out or just cancel them. So I have 2 minus a half, which is 1 1/2, or 3/2, or 1.5. All right. Now, on this problem, we could work it like we did the worksheet and do 16 to the x equals 32. And that becomes 2 to the 4x equals 2 to the 5th. But that requires me to know these powers very well, which I have to anyways. And then it says set the powers equal to each other. And then we get 5/4. But we have a new property called change of base. I can use that. 16 and 32 are both powers of 2. So what I'm going to do is I'm going to rewrite this as log base 2 divided by a log base 2. And then I'm going to put my 32 here, which we said was 2 to the 5th. And my 16, which we said was 2 to the 4th. And now we have 5 in the numerator and 4 in the denominator, and answered pretty quickly. So change of base can make these problems a whole lot easier. On the test, I don't really care which one you do as long as you show your work. All right, so let's rewrite the logarithm using change of base. In part A, we're going to use natural logarithms. In part B, we're going to use common logarithms. And then we're going to go grab our calculator. All right, so we're going to use the natural log. I personally like the natural log because it has a lot more applications in other math classes and science classes. And 2, it's a tad bit less writing. And I don't misread it and accidentally think something's a different base. I know the base is e. So the number goes in the numerator and the base goes in the basement. So with the common logarithms, we're just using log. So log of 1,000 over log of 5. So let me think about the answer. I know 5 to the 4th power square and square again. So 5 squared is 25, 25 squared is 625, 625 times another 5 is like 3,000. So something between 4 and 5. It's 4 point something. That's as good as I'm going to get without using tables or some other type of fancy math that we don't know yet. But I'm going to go grab a calculator and get the answer to as many decimal places I'm asked to do, which in this case is going to be 4 decimal places. Okay. All right. So we're asked to find the log base 5 of 1,000. Now, I have the natural log right here as one button, or the common log right above it. So I don't have that button just nice and easy and available. So I'm going to have to evaluate this using change of base. So let me put my number, and then I'm going to divide, or I can use my fraction key, alpha y equals number 1, and then put in my natural log of my base. And I said it should be between the 4th and 5th power, and we see what it's equal to. So it's approximately 4.2920. They say go to 4 decimal places, and that's what I'm going to do. You can round or you can truncate. I don't care. So now what we're going to do is we're going to do the same thing, except for I'm not going to use the natural log. I'm going to use the common log instead. So I'm just going to change my log button. And this is what we proved earlier when we proved the change of base formula, that the base doesn't matter. We can evaluate any logarithm using any base. Should get the exact same answer. Okay? So here. My answer is the same thing. 4.2920. Okay, so as we can see, it doesn't matter which logarithm you use, you get the same answer. Now I'm going to show you one more button in the calculator. And if you have a scientific calculator, it depends which type you have. Some have it, some don't. It'll look like little box of box. And then my graphing calculator is alpha window number 5. And you can actually type in the problem like it's written. And when you try to use in the graphing calculator, that's how you're going to have to use it. So we get the same answer no matter how we do this. So you can use any base you want using the change of base formula. There's a problem, a couple of problems on the test where it'll say just use a change of base formula to rewrite it. And if we say you're not supposed to be doing a calculator, that means you stop right there. And if you are supposed to use the calculator, you're supposed to write that part down and then use the calculator for the rest of it. The answer for the decimal answer, that is only worth one of the points on the calculator part of the test. The rest of the points are the change of base formula. All right, so let's talk about how to condense and expand these expressions using the properties. Now, when you're doing your homework in 4.4, it feels like this is kind of like pointless, like exercise, or like, why am I just doing this? We'll find out the real reason of why we condense and expand with these variables and expressions like this when we get into solving equations, or for those of you that are moving to math analysis, or eventually some of you will have to take calculus, you just don't realize it. You'll use these properties to make problems a whole lot easier and manageable and even possible in those other classes. But for you specifically, tomorrow's lesson, solve equations, we have to be able to either expand in some situations or condense in others. So let's just expand each expression into multiple logarithms. The one on the left is what you would see on a quiz and test. The one on the right is what you're going to be forced to do to be able to solve some problems in the next assignment. So right here, I'm trying to first figure out how many logarithms can I break this into. I can only break it into different logarithms using multiplication or division. So I have 4 things that are being multiplied or divided. The ones that are being multiplied in the top, those, remember, logarithms are exponents. So to have something in the numerator, you have to have a positive exponent. To get it in the denominator, it's a negative exponent. So when we're multiplying these logarithms, we know we're going to add those. Now, the ones after the division, we're subtracting. Now, I know some people go, okay, you subtract, and then I'm going to add for this one. Well, if you want to do that, you have to use parentheses. If you want to get it done in a shorter step, say, hey, these are both in the denominator. They both have to be negative exponents, so they both have to be negative logarithms. So if you want to do subtract and then add, you'd have to use parentheses, and after you distribute, you're right here. So we have log base 3 of z to the 7th for our last exponent. We're not done yet. When they say expand, they want to take these powers and we want to bring them out in front. Now, if you have a number here, you're supposed to evaluate it like you normally do. So 3 to what power is 9? 3 squared. So it's 2. You could make this 3 squared, bring the 2 out, and write log base 3 of 3, but then you're expected to simplify the log base 3 of 3. So we just bring the power out in front. So you raise an exponent to an exponent, you multiply the exponent of 5, and the logarithm, which is an exponent. And we are done. So when you get good at these, they're 2-step problems. All right, let's take a look at the next one. Parentheses are important. So expand it. We're going to take this exponent and bring it out in front. So when they say put in multiple logarithms, they want you to expand it and they want you to pull all the powers in front. So we have parentheses, the quantity x plus 3 times the natural log of 2. Now the natural log of 2 is just a number. It's like 7. So what you do is you just distribute. We have x times the natural log of 2 plus 3 times the natural log of 2. That becomes very, very important skill for the next section. All right, so let's work backwards. Let's condense this. Let's get this down to a single logarithm. If we want to do this as a single logarithm, you got to pop all your powers to the top. So that's going to be an x squared. That's going to be the root of y. That's going to be z to the 5th. Leave the minuses as minuses, leave the pluses as pluses. The only problem is that 3. Well, I need to make that a logarithm. So what I'm going to do is I'm going to multiply by a fancy 1, which is log base 10 of 10. Then I'm going to take the 3 and pop it up as a power. So the first one becomes the common log of 10 cubed minus the common log of x squared minus the common log of the 5th root of y plus the common log of z to the 5th. And then I'm going to put this as one logarithm. The only time you're multiplying or dividing logarithms, the only time you're going to do that is when you're doing change of base or just set up that way. So this is one logarithm. Everything's going to go inside that logarithm. So remember, logarithms are exponents. So if it's a negative exponent, it's going to the bottom. So we have x squared times the 5th root of y in the bottom. Don't put addition or subtraction in between any of these terms. So now we have what? 10 cubed, which is 1,000, times z to the 5th. And when you're good at these, you should be able to do it within 2 steps. All right, so let's see some of these problems, how they're going to be used in section 4 or 5. What they'll do is they'll put like an equal sign, put like an equal 5 or something like that on the other side. We're not going to worry about the equal sign. We got to learn how to simplify first before we can solve. So when we're adding 2 logarithms, we're adding exponents, so we multiply the exponential statement. So we have x plus 2 times x minus 1. So I'm going to go ahead and FOIL that out. So this becomes x squared plus x minus 2. When you subtract logarithms, you divide the inside. So this is log base 3 of x squared minus 2 over x minus 1. Now, if I could factor the top and reduce this fraction, I would, but I'm not able to do that. So that's all I have left to do in that problem. I'm finished. So your homework, you have the book assignment. So try these problems in the book. And then there is a worksheet, and the key is posted in OneNote or in Schoology. Just depends on how you how we set it up in your class. Things that you should be able to expect to be able to do for the quiz on this. You should be able to expect to evaluate a couple of logarithms without a calculator. Use the properties. You should be able to expand and condense expressions. You should be able to simplify some very basic expressions. And then we'll take a look at a couple other problems I think in your quiz come from the homework, and it's problems that will say something like evaluate using log base 2 or log base 5 or common log of 2 or common log of 5. They'll give you a couple of known facts, and they're going to expect you to calculate with those. You just need to use the expressions to rewrite those in what they give you.